Chapter 8.2, Arithmetic Sequences and Partial Sums. Let's start this chapter by getting a definition of an arithmetic sequence. An arithmetic sequence is a sequence whose terms have a common difference, and that common difference is usually designated by the letter D for difference. Arithmetic sequence. The difference between consecutive terms is the same. So the sequence A1, A2, A3, A4, and so on until we get to the general term AN is arithmetic if and only if or when there's a number D, that's the common difference, such that, well, what is D? A2 minus A1 is the same as A3 minus A2, is the same as A4 minus A3, ... which means A56 minus A55 is also equal to D. It's the next one minus the previous one. If that is the case, and all of these give us the same difference, then we call D the common difference. If I'm given the general term AN, that's A subscript N, is equal to 4N plus 3, I know immediately that it's going to be an arithmetic sequence, or it's going to generate one, because this is to the first power, or we could say it's linear. So if I have a linear equation, I know, oh, that's an arithmetic sequence. So look at the power of this general term. This is an explicit general term because I could put in 1 for n and get 4 times whatever n is plus 3. Well, I put in a 1, I get a 7. If I put in a 2, I get 4 times 2 plus 3, which will give us 11. If I put in a 3, I get 4 times 3 plus 3, which is 15. If I put in a 4, I get 4 times 4 plus 3, which is 19. So my first 4 terms are 7, 11, 15, 19. Those are the terms. Well, this is the first one I come to, so it's automatically A1, A2, A3, A4. Now I can test that. I'm asking myself, is A2 minus A1, 11 minus 7, the same as A3 minus A2, which is 15 minus 11, the same as A4 minus A3, which is 19 minus 15, which is 4. Because these came up 4, 4, 4, and if I continued on and on and on, I'd still get 4 as my difference. We say the common difference is 4. Now, what do we do with that common difference? If we're taking little bunny jumps between the terms, look at the size of each of these bunny jumps. The size is the common difference because to go from one term to the next, I have to add 4. Now, AN equals 4N plus 3. What's great about this explicit term? If I want to find A100, I don't have to find A99. I can just jump to putting in 100. That's the benefit of an explicit term, which is 403. Notice, I can jump around the chessboard. Here's another example of an arithmetic sequence. I'm given the general term of an explicit formula. AN equals 7 minus 5N. Well, because this is linear, because it's to the first power, I know I'm going to get an arithmetic sequence when I plug in my numbers. If I put a 1 in for n, I'm getting a 1 here. 7 minus 5 is 2. If I put a 2 in, I get 7 minus 10, which is negative 3. If I put a 3 in, I get 7 minus 15, which is negative 8. If I put a 4 in, I get 7 minus 20, which is negative 13. If I put a 5 in, I get 7 minus 25, which is negative 18. Notice 2, negative 3, negative 8, negative 13, negative 18. That's for A1, A2, A3, A4, A5. How do I know to name them like that? Well, it's the first one I can't come to, so I always start with A1. And this goes on and on. We're not limited here, so that's an infinite sequence. -3 minus 2. Well, the jump here is -5. -8 minus -3. The jump here is -5. -13 minus -8. The jump here is -5. -18 minus -13. The jump here is -5. I can also confirm that A2 minus A1 is the same as A3 minus A2, is the same as A4 minus A3, is the same as A5 minus A4. They're all -5. So my common difference is -5, and I confirm that I have an arithmetic sequence. But I knew that immediately when my exponent there was 1. It's linear. Here's yet another arithmetic sequence. If our general term of an explicit formula is 1/4 times n plus 3, I know immediately it's arithmetic because this is linear. So when I plug in my numbers, I'll put out 1 here. 4 is 3 plus 1 times 1/4 is 1. If I put a 2 here, I get 3 plus 2 is 5 times 1/4 is 5/4. If I put a 3 here, I get 6/4, which simplifies to 3/2. If I put a 4 here, I get 7/4. And if I put a 5 here, I get 8/4. You know what? Perhaps this is better if I leave this as 6/4, and if I leave this as 4/4. Perhaps that will help us see the pattern more clearly. 4/4, 5/4, 6/4, 7/4, 8/4, and this is an infinite sequence. So the first one I come to is A1, then A2, then A3, then A4, then A5, etc. Well, when I do A2 minus A1, 5/4 minus 4/4, of course that's 1/4. And I do 6/4 minus 5/4, of course that's 1/4. And 7/4 minus 6/4, of course that's 1/4. And 8/4 minus 7/4 is 1/4. So the telltale sign of an arithmetic sequence is we have a common difference. And in this case, that is 1/4. Was it surprising at all that that was the multiplier of my n? Not at all. Is the sequence arithmetic? Well, this is the first entry or term I come to. So I'll label it A1, then A2, then A3, then A4, then A5, and it's an infinite sequence. So if I'm interested to answer this question, is the sequence arithmetic, I'm going to check out A2 minus A1, and I see that's 4 minus 1, which is 3. And then I'll look at A3 minus A2, which is 9 minus 4, which is 5. Notice those two are not equal, so we do not have a common difference, and the sequence is not arithmetic. Perhaps you will recognize that the general term of an explicit formula would be written as, I'm trying to relate 1 to 1, 2 to 4, 3 to 9, 4 to 16, 5 to 20. Oh yeah, that's whatever this is squared. Well, the general term has so much power. AN would simply be whatever is here squared. Let's try to find a general formula for any arithmetic sequence. For any arithmetic sequence, the first term will be the first term. And our second term, A2, will be the first term plus whatever that common difference is. Our third term will be the second term, or we could say the first term plus whatever the common difference was. Well, that's actually a second term plus another common difference, which would be A1 plus 2D. Our fourth term would be A1 plus D plus D plus D, or A1 plus 3D. Our fifth term would be A1 plus D plus D plus D plus D, or A1 plus 4D. Now, take a look at the pattern that's emerging. When we want the second term, we had 1D. When we wanted the third term, we had 2Ds. When we wanted the fourth term, we had 3Ds. When we wanted the fifth term, we had 4Ds. In other words, whatever term you have, the number of D's, or the multiplier on the D, is going to be one less than the term you want. So if we're looking for the general term, AN, now I've taken 5 and made it N, that's going to be the first term plus, well, whatever N is minus 1 to give us 1 less times D. And that is going to be the general term for any arithmetic sequence. AN is going to equal the first term plus N minus 1 times D. And whatever here is the term number you're looking for, you're going to have one less number of jumps. You can think of that as the number of jumps. And D will be the size of each jump. Here it is more formally. The nth term of an arithmetic sequence has the form AN equals A1 plus the quantity N minus 1 times D, where D is the common difference between the terms and A1 is the first term in the sequence.